All right, so we are back with video 2 of section 9-1, Introduction to Circles. As I had mentioned in the previous video, I'm going to go through and complete some examples for you. We're actually going to apply some of that knowledge that we learned in the previous video. So let's get started. The first problem that we're going to take a look at uses the diagram on the right-hand side of the screen. So using that circle on the right, we're going to name each of the following. So we want to name a circle. And remember, the way that we name circles is we use the center point. So in this case, the center of this circle is point A. So this circle we will call circle A. So we have the option of using that symbol, the circle with the center drawn in front of the letter A, or we can actually write out the words circle A. Okay, so either one of those would work. Letter B asks you to identify the center of the circle. We just talked about that. The center of the circle is point A. So we'll jot that down. So again, you have the option of just writing in the letter capital A, or you could write the word point A as well. Next, we're asked to name two diameters that appear in the diagram. So remember, a diameter is a chord that passes through the center of the circle. So in this case, we have the chord FC that passes through the center A, and then BD that also passes through the center A. So those two chords would be the diameters. So in this case, segment FC and segment BD, those would be the two diameters that are pictured in this diagram. Obviously, there are others that we could draw in, but those would be the ones that are pictured in the diagram. If we move this down a little bit, point of tangency. So what we're looking for is a line or a segment that's intersecting circle A at one point. In this case, that point is point D. So point D is the point of tangency. So D, or we could write point D. Okay, next we'll go up to letter E. We're asked to name 4 radii. So remember, a radius of a circle extends from the center point to any point that's on the circle. So I see 4 radii in this diagram. So here's the center. This would be one radius from A to B. Another would be from A to C, so segment AC. Another would be A to D. And then the last radius that is pictured in this diagram is segment AF. Okay, so those are the radii that are pictured in this diagram for circle A. Next thing we are asked to find is a tangent. So in this case, we already talked about the point of tangency being point D. So we need the line that passes through point D and is tangent to the circle. In this case, there's only one line that meets that description in this diagram, and that is line DE. Okay, next we want to find 6 chords. So we already found 2 of those chords, as I had mentioned earlier, so I'm not going to rewrite those. Let's save a little bit of time here. The 2 diameters are chords, so those would also be included. So these are also chords by definition. Now remember, again, chords are defined as line segments whose endpoints are on the circle. So I can see 4 of those in this diagram. I see DF, I see BF as a chord, BC, and CD. So those are the 4 other chords along with the diameters. So DF is one FB, let's try that again, FB is another BC, and then CD. So this would be 4 chords, and then with the 2 diameters, makes a grand total of 6. And finally, for example number 1, letter H, a secant. So a secant, remember, is defined as a line that intersects a circle at 2 points. And the only figure that meets that description here would be line FC. So line FC would be your secant that's pictured in the diagram. All right, so let's scoot this down just a little bit, and I might have to go back and forth a little here, so I apologize for that. Letter I asks, why is AC not a chord of A? So let's go back up and look at that diagram for a second. So why is AC, and I'm going to highlight that right now, that segment. Whoops. Let's try that again. All right, so let me highlight AC real quick. Okay, so why is AC not a chord? Well, the answer lies in something that we've talked about already. Remember, a chord has to have 2 endpoints on the circle, and in this case, AC only has 1 endpoint on the circle. So AC has only 1 endpoint, not paint, on the circle. So AC is actually a radii, or a radius of the circle. Next one, why is line BD not a chord of A? Well, the answer to that one lies in this notation. Okay, so by definition, a chord is a line segment. So line BD can't be a chord because it's a line, not a line segment. So the answer here would be chords are line segments, not lines. So technically, line segment BD is a chord. All right, so that takes, care of example number 1. Let's move on to example 2. This one asks, how does the diameter relate to the radius of a circle? Well, I'm going to write this as an equation. So I'm going to actually, we're going to come up with 2 equations here. Let D equal the diameter of the circle, and R equal the radius. So again, I'm going to express this relationship as an equation. Well, the diameter is going to be 2 times the radius. Or what we can do is we can manipulate that equation and divide both sides by 2 and isolate the radius, and we can get R equals 1/2 of the diameter. All right, and those are 2 important relationships that you use quite frequently, so make sure that you understand that. Number 3 says draw 2 concentric circles. Draw a tangent to one of the circles. Is it tangent to the other circle? Sorry about that. So what I've done is I've drawn 2 concentric circles. You're probably going to want to sketch that on your notes right now. And I'm actually going to look at 2 cases. I'm going to look at a line tangent to the outer circle and a line tangent to the inner circle. So if I draw a line tangent to the outer circle, it's going to look something like that. Now clearly we can see that this line is not going to be tangent to the inner circle. Excuse me, because in order for that line to be tangent to the inner circle, it's going to have to intersect the outer circle twice. So in this case, that line is not going to intersect the inner circle at all. For the inner circle, again, if I draw a tangent to the inner circle, Now what's going to happen is, as I just mentioned a second ago, that line's going to intersect the outer circle twice, which means it's not tangent, it's a secant. So the answer to this question is no. All right, we've got a few more problems that we need to look at. As I had mentioned at the end of the last video, we were going to talk a little bit more about inscribed, um, sorry, let me look at my notes here, inscribed polygons and circumscribed circles. So we're going to look at those right now, what that looks like. So example number 5 asks you to inscribe an isosceles triangle in a circle. So what you see here is, in order to do this, the vertices of the triangle, or whatever polygon it is that you're working with, have to be points on the circle. Okay, so again, the vertices of the polygon must be points that are on the circle, and they can't share any other points. Okay, so that's what it's going to look like for an isosceles triangle to be inscribed in a circle. The next one, you're asked to circumscribe a circle about a rectangle. So again, you're pretty much doing the same thing. And again, if you take a look, the vertices of this rectangle are on the circle. Okay, and no other points from the rectangle are on the circle. Number 7 says draw a circle with radius 6. So I drew a circle here, and I'm going to draw the center point in and make the radius equal to 6. Then says draw 2 radii, OG and OH. So I'm going to call the center O, and I'm just going to make this point G, and I'm going to make this point H. And we're saying that those two segments form a 120-degree angle. So I'm going to draw that in. And this clearly is not to scale, but it's going to give us something to look at and something to reference as we go through and complete this problem. All right. So what we're asked to do here is to find the length of GH. Okay, so I drew in GH. Now what I'm going to do is I'm going to use a few things to my advantage that I understand here. First off, radii and circle are all going to be, in a particular circle rather, are all going to be congruent to each other. So in this case, if OG equals 6, then OH also has to equal 6. So all the radii in a given circle are going to be congruent to each other. Now to try and find GH, what I'm going to do is I'm going to drop in a perpendicular here. And that's going to form a 60-degree angle up here and another 60-degree angle up here. So what I've actually formed are two 30, 60, 90 triangles. And the altitude that I dropped in is the short leg of a 30, 60, 90 triangle. So that altitude has to equal 3. And then this other part of GH is going to be the long leg of a 30, 60, 90. So that's going to be 3 root 3. So GH is going to be 2 times that, which is 6 root 3. And the reason why it's 2 times that is because when we dropped in this altitude, that's the altitude of to the base of an isosceles triangle. It cuts that base in half, so it makes 2 congruent pieces. So we know that the total length of GH has to be 3 root 3 plus 3 root 3, which is 6 root 3. Let's take a look at number 8 now. Number 8. This one's really, really straightforward if you know your Pythagorean triples. The way that I would solve this to find x is I'd look at this small right triangle here. One side of that right triangle is 3, so one leg of that right triangle is 3. The other leg is 4, so x has to equal 5. Now, if you don't remember that Pythagorean triple, you can always use the Pythagorean theorem and do 3 squared plus 4 squared equals x squared, and you're going to end up with x equals 5. Letter B, if we look and see, and I'm going to call these points H and G, so we have a reference. So if you look, triangle HOG has to be an isosceles, I'm sorry, not an isosceles triangle, an equilateral triangle, and equiangular, because these base angles are congruent, because the radii make this isosceles. So all three angles are going to equal 60 degrees, which means x is going to have to equal 6 to make that an equilateral triangle. Our last one, again, the radii are congruent, so this side has to equal 4. Now this is an isosceles right triangle, which means these angles, these interior angles, are 45 degrees. And again, if we remember our 45, 45, 90 triangle relationships, the hypotenuse is equal to the leg times the square root of 2, so x is going to have to equal 4 root 2. Okay, so I hope this was helpful. You're going to get some practice problems assigned. Again, as always, if you're running into any issues, any problems, make sure that you email me with questions.